Welcome to this explainer. If you've ever looked at a gleaming, high-speed rail network and wondered why those lightning-fast passenger trains and the heavy freight trains simply cannot share the exact same tracks, you are in the right place. It's a question that honestly plagues transit planners all over the globe, and the answer? Well, it's this incredible mix of physics, logistics, and raw power. Let's dive into it.
It seems like a total no-brainer at first glance, right? Why shell out billions of dollars laying down entirely new corridors of steel when we already have these massive railway networks crisscrossing our countries? Well, today we are going to unpack the undeniable physics that prove why doing that is mathematically, financially, and practically impossible if we want to maintain maximum capacity and absolute safety.
So here is our game plan for today's explainer. First, the mixed traffic dilemma. Then, the logistics clash. After that, the physics of the curve, followed by wear, tear, and air. And we'll wrap it all up with the segregation strategy.
All right, starting us off, Section 1, the mixed traffic dilemma. Let's look at our track usage options. We essentially have 4 ways we can run trains across a network. It's kind of like a sliding scale. Up at the top, in case 1, you have total segregation. High-speed trains stay strictly on high-speed lines, and classical trains stay on classical lines. But as you move down to case 4, you see complete intermixing, where all types of trains run on all types of lines. And while systems in places like Germany and Italy have historically tried mixed models, it sets the stage for some massive constraints. Because honestly, when you choose intermixing, you are inviting chaos.
Moving right along to Section 2, the logistics clash. Let's talk about the speed conflict.
Here is the wild thing from a pure logistics standpoint. If you slip just one single high-speed train, we're talking traveling at over 300 kilometers per hour, into a conventional, slower train schedule, it literally eats up the operational path of 3 or more freight trains. Let that sink in. You aren't just adding a fast train to the tracks, you are actively deleting the capacity for freight.
Picture this on a timeline. At minute 0, a slow freight train rolls out. 15 minutes later, a high-speed passenger train departs on the exact same track. By minute 30, that high-speed train has entirely caught up to the heavy freight ahead of it, forcing a massive system bottleneck. So you basically have 2 terrible choices. You either force the freight train onto a side track to wait, which totally kills its efficiency, or the high-speed train is forced to crawl behind it, completely neutralizing its own speed advantage.
Okay, Section 3. The physics of the curve. Let's get into track geometry and cant.
Now, to really grasp track geometry, we have to talk about cant, also known as equilibrium superelevation. Think of a steeply banked curve on a NASCAR racetrack. That cant is absolutely essential to keep a train from flying off the rails when it takes a turn. The track is literally tilted inward. But here's the catch. The exact angle of that tilt is entirely dependent on the speed of the vehicle.
Let's put this into perspective with a standard curve that has a 4,000-meter radius. The physics here mathematically forbid any sort of compromise. A heavy freight train cruising at 80 kilometers per hour requires only 19 millimeters of cant. But a high-speed passenger train taking that exact same curve at 300 kilometers per hour, it requires a massive 265 millimeters of cant. If you try to invent an intermediate bank angle to, sort of split the difference, it dangerously exceeds the safety limits for both train types.
Looking at these numbers, you can easily see why providing a track geometry that safely accommodates both 19 millimeters and 265 millimeters simultaneously is literally an engineering impossibility. If the track is banked up high for the fast train, the slow freight train will tip inward, putting immense, destructive weight on the inner rail. But if it's banked low for the freight train, the high-speed train is at a huge risk of derailing right off the outside. You just can't negotiate with gravity.
Which brings us to Section 4, wear, tear, and air, the harsh realities of safety and maintenance.
Let's talk about sheer mass for a second. Heavy freight locomotives are absolute beasts designed for raw pulling power, and they exert a brutal, bone-crushing 23 tons of axle load downward onto the steel rails.
Now, contrast that massive weight with a high-speed train, like the French TGV. High-speed rail sets are strictly capped at just 17 tons per axle. Why? Because flying along at over 300 kilometers per hour requires absolute perfection in the track, and lighter axles are what preserve those microscopic track tolerances. So if you run those 23-ton freight beasts over our pristine, highly tuned passenger corridors, it makes it impossible to maintain the flawless track geometry required for safe high-speed travel. Studies have proven that heavy freight quite literally beats the high-speed track alignments right out of place. That makes it incredibly dangerous to then send a passenger train rocketing over it at top speed.
And hey, if the track wear didn't convince you, wait until we talk about the aerodynamics inside enclosed spaces like tunnels. It is terrifying. When a train enters a tunnel, it pushes a wall of air ahead of it, acting almost like a massive piston.
The sheer aerodynamic violence of mixing these two types of traffic inside a tunnel is staggering. Imagine a high-speed train and a freight train passing each other going opposite directions. The relative speed difference can hit up to 700 kilometers per hour. That creates an explosive burst of air pressure when they first pass, immediately followed by a vacuum-like drop. These micropressure waves severely stress the passenger train's windows. And even crazier, the sudden shockwave of air can literally destabilize the heavy freight. We're talking violently ripping off cargo covers or shifting entire loads. To avoid an aerodynamic disaster, engineers are basically forced to either drastically reduce speeds or just separate the trains entirely.
All right, our final section, the segregation strategy, why this is the ultimate win-win. So, by building entirely new lines strictly for fast passenger trains, we don't just solve all those physics and aerodynamic nightmares we just talked about, we actually strike an economic goldmine. Yes, it prevents the heavy freight from destroying the new passenger tracks, but crucially, by pulling the passenger trains off the legacy networks, we release massive path capacity on those older lines. They are suddenly freed up to carry way more heavy, profitable freight without having to constantly yield to high-speed passenger schedules.
This quote really hits the nail on the head. The whole philosophy of modern rail infrastructure really boils down to this: separating the extremes optimizes the whole shebang. It is an incredibly elegant solution where building a brand new, exclusive track actually breathes incredible new life and profitability into the old one. So as global traffic demands absolutely surge, it leaves us with a pretty provocative question about how we design our cities and transit networks going forward. We often tend to think that integration is always the answer, but the relentless logic of track geometry, speed, and aerodynamics proves that sometimes the absolute best way to bring a thriving, high-capacity transportation network together is to meticulously keep its components apart. Thanks so much for joining me on this explainer. Keep learning and keep looking closely at the invisible systems that move our world.